Press record, and there we go. All right, hi guys. Welcome to week 2 of CLAS. This is going to be the more theoretical aspect. So as I mentioned before, Mondays are going to be more conceptual, and then Wednesdays are going to be actual review of problems that pertain to what I just lectured over. So with that being said, week 2 of the class, right, is going to be about preferences. Preferences. Whoops. If you remember last week, we talked about the budget constraint. And so that's what you're able to afford, right, for any given combination of X1 and X2, which we called bundles, right? So we have a given level of income. And so with that income, we're going to be able to allocate between 2 different goods. And so that line that we drew, right, was the rate at which we could exchange each of those 2 goods while still being able to be affordable, right? Having those 2 multiplied by their respective prices be equal to income. Now, if you remember, I made a comment about how affordability and preferences are very different things, right? In that we're constrained by what we can afford, but that doesn't give an indication as to what we prefer, right? So, and given that information, the goal of this class is going to be to maximize our preferences, so be as close to what our preferences can be, while still being able to afford it, right? Because we can't go past that range of affordability. So, given this information, I wanted to talk about the concept of indifference curves. So, you guys have surely been introduced to the idea of an indifference curve. And so there's going to be different kinds of them. But throughout the kind of idea of those curves, no matter what shape they are, one thing is always going to be true about them, and is that every point along that curve represents some level of utility, right? We call it utility, no matter where you are on that curve. So let's just kind of go into them. We have perfect substitutes, which are going to look something like this, where we can make a kind of linear connection between those 2. So whatever this slope is, right, is going to be an indication of how we value one good relative to another. And so as I mentioned before, it's key that you guys are aware of the fact that this point right here provides the same utility as this point right here, okay? And so to kind of tie back to the budget constraint, if you remember, every point along that budget constraint added up to the same amount of income, right? Or yeah, I guess we'll just leave it at income. And so in this case, each point along this curve is going to correlate to the same value of utility, right? But because of the fact that our preferences, right, are unlimited, we're going to have infinitely many indifference curves, right? But the key thing about them is that this ratio is going to stay the same. It's just, the utility that's going to be a resulting of that. So you can kind of think of this as being U1, right? So utility 1, this is utility 2, right? And utility 3. I wouldn't get too confused about the fact that we have these infinitely many utility functions. They're going to come in handy, though, when we talk about how there's only going to be one single one of these indifference curves that's going to be able to match up with the unique budget constraint that we have, right? And so you guys are hopefully going to be able to see that as we move forward. The next one I want to talk about is perfect complements. And so these are the ones that I kind of introduced in last Wednesday's lecture, right? Where I went over a practice problem that involved perfect complements. And then the classic example of those is left shoe, right shoe. And you can obviously kind of extrapolate from that different examples of what perfect complements would be. And I definitely recommend you do the same for perfect substitutes. Kind of a general perfect substitute is blue pen black pen, right? You don't really care which pen you have because it provides the same function, right? So say that, and this is kind of going back to the perfect substitutes, say that you had the choice between blue pen and black pen where you don't care, right, which one you have. If blue pens are cheaper, then it's going to make more sense to purchase all of blue pens because you get that same amount of utility for a cheaper price, right? Or if you kind of think about it that way, you get more utility for the same price. So hopefully you guys can kind of see where I'm going with that. And it's not necessary that they have a one-to-one relationship. It's possible that you like blue pens twice as much as you like black pens, but if blue pens are 3 times as expensive, right, as black pens, then that's something that you have to think about when considering which one you want to purchase more of, right? So that's going to kind of come in handy when we relate the concept of a budget constraint and our concepts of utility. But hopefully you guys kind of get that. It's not necessarily about which good provides the more utility per unit, right? The marginal utility. There's a lot of different other factors that are going to play a part in that. So apologize for my tangent. Let's move on to perfect complements. You can go ahead. Perfect complements, right, are going to be these L-shaped indifference curves that, maybe I'll use a deeper marker. There are these L-shaped indifference curves that we see, right? And it's very similar to perfect substitutes. We have infinitely many of these. And so you kind of want to think about why it is that they're L-shaped, right? And so the classic example, so if you want to think about the utility function that would go with this, utility is equal to, say, x1 plus x2, right? Where you have this linear relationship between x1 and x2. In this case, the perfect complements are going to follow the min function, right, between x1 and x2. And so because of this relationship that we have right here, right, it makes no sense to have like way more of x1 than x2, simply because your utility is just going to be the lowest value within these brackets, right? So that's why you want these to be about as equal as possible, if not completely equal, right? So the example that I used before, if you have 2 right shoes and you have 5 left shoes, you can still only make 2 pairs of those shoes, right? And those additional 3 shoes that you bought cost money. And so
wasn't charging.
Sorry. Oh, this button right here. So yeah, essentially, it makes sense to have these 2, right? These 2 values, and this is just a 1. So actually, I'll make this a 2, and I'll make this a 2. You want these to be as equally lined up as possible, right? And it won't necessarily be the case that they're lined up. So say that we're making a desk. It's possible that a desk is made up of 4 nails and 1 piece of wood. I mean, that's not how you make a desk. There's more that goes into that. But for every piece of wood, you want 4 nails. And so the combination of 4 nails to 1 desk, right, and any sort of multiplicity, so 8 nails and 2 desks, or 2 pieces of wood, 12 nails, 3 pieces of wood, right? That's kind of going to be the relationship between the 2 that you're going to have, right? We have other indifference curves. These ones I wouldn't worry too much about. You kind of want to just be able to know what the indifference curve looks like. So let's say that x1 is a good and x2 is a bad, right? Instead of having these downwards sloping indifference curves, and so the reason they're downward sloping is because it indicates that you have to make a trade-off between the 2 because of the fact that they're both something that you would want. Whereas with a bad and good relationship, these are going to be the indifference curves that go along with that, right? And so you're going to want to kind of look at what this graph shows and analyze which one you think provides a higher utility, right? Do you think this one provides a higher utility, or do you think this one provides a higher utility, right? And you're going to have to make this or I guess what I would say is you're gonna have to be able to think through this when the axes are flipped, right? So if this was a good and this was a bad, how would this look, right? Which would be the indifference curve that provides more utility. And so what I like to do in these situations is kind of just hold the bads at a certain level, right? So assume that we have this many units of a bad good, right? Well, if we have these kind of this given amount of bad, we're going to want to have more of the goods to kind of outweigh this negative effect that we're going to be given, right? So obviously, you have more goods here than you have here, and you have more goods here than you have here, right? So that's going to tell us that this indifference curve right here is going to be better than this indifference curve, which I'll highlight in green, right over here, okay? So that's kind of what you want to think about conceptually. When you look at a indifference, or sorry, if you look at a utility function, the goods could be something like x1, and then the bads are going to be typically minus like 5x2, right? For whatever something. The key point is that the marginal utility, which we'll get into in a bit, the marginal utility of bads are going to have this negative sign, right? Which pretty much says that for every bad that we add, our utility overall is just going to go down. And so the same kind of thinking follows for neutrals. So a neutral good, instead of having these upward sloping lines, is just going to be these vertical lines, right? So good and neutral, right? And so you don't really care how much of each neutral you have, right? It's neither good nor bad. But what you do care about is having more of the goods, right? This concept of monotonicity, right? That you guys have surely heard. And that kind of goes into the idea of having well-behaved preferences, is that you want more of units that provide value to you, right? So you want more goods. So this is kind of the thinking that applies to that. There's going to be two more indifference curves. Or actually, there's one more that is kind of supplementary that I think you should be aware of. And then there's going to be the one that is most important to you guys, which is going to be the Cobb-Douglas, right? But first, before we get into Cobb-Douglas, let's get into satiation, right? So the way I like to think about satiation is a single given point that's already going to be the predetermined best point for you, right? This is going to be what provides the highest utility. And so everything that kind of is away from this is going to be less good, right? You want to be as close to this point as possible. And there's actually a lot of goods that follow this idea of satiation. Typically, I like to think about it as you're at an all-you-can-eat sushi buffet, right? Where obviously, because you've prepaid for it, you want to eat as much as possible. You've kind of been looking forward to this for a while. But you know how it goes. After a while, you order too many rolls, and they say you have to pay for the rolls that you don't eat. And so you eat way too much. And so you were here, you're creeping up to here, right? And once you get here, this is ideally where you want to stop. But because of the fact that you have to pay for the rolls that you don't eat and you ordered way too many, right? You end up over here, right? Which means that you're actually farther away from this best point, even though you consumed more, okay? And so this is the idea of satiation. Typically, when I see these, the utility function looks something like x minus 5 squared, for example. Actually, is that what they look like? No, something like this, right? This is an example of something that would be like satiation for x, in that because of the fact that there's a negative sign attached to it, you want this number to be as small as possible. And so that's kind of going to be what is driving your idea as you solve the problem, right? You don't want to have this negative marginal utility. And so the way that we can kind of combat that is having x be as close to 5 as possible, because or else we're just going to have a greater magnitude that's attached to the negative sign. So it's going to be negative utility. Okay? So that's kind of the idea of indifference curves. What I would say is that the most important part about the indifference curve is the fact that every single point along that curve provides the same utility, right? So if there's one thing that you kind of take away from this, it's that information. Now, going into the Cobb-Douglas, which is going to be kind of the flagpole indifference curve that you use. Ah, man, my knees always hurt when doing this. So the thing that I want to kind of talk to you guys about Cobb-Douglas is all of the kind of the calculus. So that's why your textbook has calculus applications. I promise it's not too complicated, but because it's a continuous function, right, there is some calculus that you're going to be able to apply to it. So what you guys have, oh, gee, I can't use this one. I can use this one. So what you guys have seen so far is that a Cobb-Douglas typically is going to have this shape right here. So the reason why it has this shape, well, first off, it's downward sloping, indicating that both x1 and x2 are goods, right? And it's also, you know, there's this idea, right, that actually, before I get into that, this is going to be your Cobb-Douglas, okay? So take a step back. The cool thing about Cobb-Douglas, as I mentioned before, is that there's a calculus application that's going to allow us to easily optimize, right, between a combination of x1 and x2. And so one of the inputs that goes into optimization is this idea of rate of substitution. Okay, and so the rate of substitution is how we measure x1 and x2 relative to one another, right? So let's say that this is kind of the graph that we're working with, 1, 2, and 3. This is 1, 2, and then this is a half, right? So let's say that we start off right here. This is the point 2, 1, right? And we go to, let me draw this a little bit lower.
You mean 1, 2?
Yeah, sorry, I apologize. This is 1, 2. My bad, guys. So this is 1, 2. This is, pretend that this is 2, 1, even though it's not exactly drawn to scale. This is 2, 1. And then this is 3, 1/2, right? And so this rate of substitution, if you notice, is not constant, right? It's going to be changing as we move along this curve. So we're going to call this A, we're going to call this B, and we're going to call this C. So going from A to B, think about we're getting more of x1, but we're giving x2, right? So in this situation, we had to give away 1x1, or we got 1x1, but we had to give away 1x2, right? Hopefully you guys can see that. And going from B to C is going to be a different relationship, right? We received 1x1, but we lost only a half of good 2, right? Negative 1/2 x2, right? And so what's going on here, and so don't think about this as a slope, think about this as just a ratio of what you had to give up, because we all know that slope is rise over run. So if we're actually looking at the slope, slope is equal to -1, and the slope in this case would be equal to -1/2, right? What you notice is that we had to give up more of x2 to get an additional unit of x1 when we had less x1 to begin with, right?
Wouldn't the slope be -2?
What's that?
From B to C, wouldn't the slope be -2?
No, because, right, if you think about slope as being rise over run, the rise is -1/2, and the run is 1, rise over run. So you rose -1/2, right? You rose -1/2 and you ran 1. So multiply through by 2 and it's 1/2.
Oh, because you have 1 over -1/2 and that. And
Yeah, so it's a little
fraction.
bit misleading. This right here, this is not an expression of slope, right?
Oh,
This is just an expression of the ratio that you had to give up, right? So I guess it was a little bit misleading. Hopefully
yeah,
I
no,
tried
that
to
makes
clarify
sense.
that.
Yeah.
But this is something that you'll notice with Cobb-Douglas is that there's this idea of kind of this rate of substitution changing as we get along the curve, right? And so kind of you can relate this to your own life, right? Where if you are, say, in a desert full of nothing but arid air, you would pay a lot for that first water bottle. You would probably pay a lot for that second water bottle. But once you have 100 water bottles, are you really going to be paying as much, right, for that 101st water bottle, right? There's going to be diminishing returns to how much, right, you're going to be getting. So this concept kind of relates to this idea of diminishing marginal rate of substitution, right? In that as we move along this x-axis, or I guess x1 axis, the rate of substitution is going to be slowly decreasing, right? So the rate of substitution was -1, and then it goes to -1/2, right? And if you think about it in infinitely small intervals of x1, right? Which implies that there's going to be calculus involved, right? That's how we get this idea of diminishing marginal rate of substitution. Is everybody good with that?
Yeah, that makes sense. Like a
Right?
limit.
So yeah, basically as the limit approaches 0. So the limit, and I hate using this notation because I think it's unnecessary for econ classes to just go full math notation on you. But the change in x1 approaches 0, right? This is kind of essentially what we're talking about when we talk about these infinitely small intervals of x1, right? So with that being said, when a Cobb-Douglas equation, right, is truly Cobb-Douglas, you're going to get dMRS, which essentially says that your MRS decreases as x1 increases, or your MRS decreases as x2 decreases, right? And so with that being said, I want to get into the idea of what MRS is, just because it hasn't necessarily been covered. Well, so it has been introduced, but not in the way that you necessarily are familiar with it yet, okay? So this idea relates to marginal utility. So we look at marginal utility, and I think that I've probably said the term marginal utility before, but I just want to kind of formalize it. Marginal utility is kind of defined as keeping x2 constant. It is the added utility from one more unit of x1. And you can kind of apply this to the marginal utility of x2 as well. This is the marginal utility of x1. And so this is saying that I'm consuming the same amount of x2 as I was beforehand, but I'm only increasing my consumption of x1, right? It's how much that extra unit of x1 adds to my overall utility. And so you might see it expressed as something like this: utility of x1, x1, x2 over, right? So mathematically speaking, this is the change in the utility as a function of x1 and x2 over the change in x1, right? So this is going to be the marginal utility of x1, and you would basically just swap x1 for x2 if you're finding the marginal utility of x2. Why do I bring in the idea of marginal utility? This is because the idea of marginal utility goes into the whole thing that I was talking about how you exchange one good for another, right? So, right, as I mentioned before, if x1, say, provides 5 units of utility, right? All right, let me take a step back. Say that the marginal utility for x1 is 5, meaning that if I have one more unit of x1, I'm going to have 5 more utility, right? And that the marginal utility of good 2 is 1, meaning that if I add 1 unit of good 1, then I get 1 unit of utility, right? I'm going to need 5 units of good 2 to equal this amount of utility that I get, right, for having 1 unit of good 1. Does that make sense kind of internally for you guys? And so this relationship that I just talked about is going to be how I make that decision, right? Because if you remember, every point along this curve right here, my indifference curve, has the same utility. And so in order to kind of go from here to here, I need to keep evaluating how I value one good relative to another. And that relative comparison is done through marginal utilities, right? You basically want to compare, well, how much better off am I with this good versus how much better off am I with this other good, right? And how many of one good do I need to equal being as good as 1 unit of the other good? And I know that's really wordy, so kind of try to break it down in words that kind of make more sense to you guys. But that's essentially what I'm trying to say with the idea of marginal utility, right? And so relating what we know about marginal utilities and making the connection between this and my MRS, MRS, which is the marginal rate of substitution, right, is going to be defined as the negative marginal utility of good 1 over the marginal utility of good 2, right? And so because of this, right, I've kind of mentioned how this ratio of marginal utilities equals the slope that we were working with, right? Because I kind of talked about how to go from one point to another, that's going to be the comparison that you have to make. And so when we're dealing with infinitely small changes in x1, this is basically just going to be the slope at any given point of our indifference curve, right? So I think that this is really important for you guys to kind of hear again, is that our MRS is the slope of our indifference curve at any given point on the curve, right? So 2 takeaways. The MRS is the slope of the indifference curve. And the second takeaway is that any point along the indifference curve provides the same amount of utility, okay? So hopefully you guys kind of are able to absorb that. Are there any questions about that? So that's a good question. Here. So you would kind of intuitively think about how this would have to be the marginal utility of good 2 over the marginal utility of good 1. I'm trying to think from a mathematical point of view whether I have a good explanation as to why that is. But so I think it's because of the fact that these marginal utilities refer to how much utility you get from one good. So actually, I do think I have a good explanation. So say that my MRS at this point right here is -5, right? And so when my marginal utility, or when my MRS is -5, that means that the ratio between the marginal utility of good 1 over the marginal utility of good 2 is -5 to 1, right? But in essence, what this means is that I need 5 units of good 2 for every 1 unit of good 1, right? In order to preserve that utility. Does that kind of make sense? How that kind of backwards organization of x1 over x2 instead of x2 over x1 makes sense, right? Say that the MRS is -4 here, right? So previously we had 5 x2 for 1 x1, right? Now we have 4 x2 for 1 x1, right? And so, and this is just the ratio, right? Like a 5 to 1. This could easily be 20 to 4, and this could easily be 20 to 5, right? Just kind of working it out. But I think that the reason why this is the marginal utility of x1 over marginal utility of x2 is because of that idea that because they simply are meant to depict marginal utilities, it's different, right, than the actual x1 and x2, right? So the marginal utilities are a function of how much x1 and how much x2 I have, right? But it doesn't mean that I have, say, 5 more x1 than I have of x2, right? I'm trying to think whether that was the best way of explaining it. Are you still confused about that? Is anybody confused about that? Because I could definitely try to go at it again.
So would you say that's like based off of proportion? Or
Could you say that again?
would you say that's based off of proportion?
So yeah, this is based off of the proportion, right? So MRS is the proportion between the two marginal utilities. But what I'm trying to say is that this connection between the marginal utilities is not a one-to, or it is a one-to-one, but it's not a one-to-one in the way that you would think about it in terms of how much x2 and how much x1 I have, right? So typically slope is rise over run, and this would appear to be run over rise, right? But what I'm trying to say is I wouldn't think about it in that light because of the fact that this isn't the actual number of good 1 and the actual number of good 2 that I'm working with. Does that make a little bit more sense?
Yeah, thank you.
Okay. And if there's definitely more questions, feel free to ask up. Because I do think that this concept is one of the more kind of complex to figure out. And it's like the basis for everything that we're going to be doing going forward. So it's really important that you memorize kind of what is going on here. And what I will say is that you don't necessarily need to have it totally memorized why things are going, like why it is that this is x1 over x2 instead of x2 over x1, right? You can totally make it through this class with just memorizing the fact that it is instead of why it is. So yes. Yeah. Well, marginal utility implies that it's only for one good increase, right? So if you go back to the definition of marginal utility, it implies that it's the marginal utility for one unit increase. So that's exactly right, Giovanni. Kind of to go off of this, right? This idea of preferences. We've talked about preferences and we've talked about the budget constraint. I want to quickly kind of talk about how we're going to be able to maximize, right, our preferences given our budget constraint, which is kind of what I've been talking about this whole time, but now we're going to be able to formally make that connection between the two. Before I do that, are there any questions about the idea of preferences just as like a standalone topic? I will take that.
I have a quick question.
Yeah, go ahead.
At the bottom of the screen, you have written 5x2 for, they both look like x2.
Oh, they are, because they are. Because they
are.
are.
Okay, yeah, gotcha.
Because they are. That's
Perfect.
Just me being careless. I apologize.
No, that's all right. I was just
and thanks for stopping me.
No worries.
But yeah, so everything else still stands. Hopefully, if you were confused about that, it clears up some confusion. But so with that being said, I do want to talk about kind of the general steps you're going to take when you maximize your bundles or your bundle, or finding the optimal, I don't know, whatever the expression is. To answer your question, Giovanni, I actually don't really know, if I'm being quite honest, what it looks like. I know that with a quasi-linear, there's going to be a flat part, and then there's also going to be a curved part, but I've never actually been able to draw them, nor have I been asked to draw them, nor have I seen a question where you're asked to draw them. It kind of is, the quasi-linear questions do pop up a lot, which is why I think it's good that you are familiar with it. But they don't necessarily pop up in the way that you'd really need to know it visually. It's more just kind of the mathematical expression of what quasi-linear is what you kind of need to be familiar with. And I'm definitely going to go over some questions probably this Wednesday, if I do, about how you can solve those quasi-linear questions. But that's a good point. So, and that's also, it's one of the indifference curves that I didn't do at the beginning, but it's still very important. And so I guess while I have this time talking about the indifference curves, I'll say that the most important three that you'll want to know are the perfect complements, perfect substitutes, and Cobb-Douglas. And definitely Cobb-Douglas, most important of all. But a close fourth is quasi-linear, because I have seen a lot of midterm exams and final exams that do utilize that. But the mathematical reasoning behind it is still the same. So that's all you really need to know. So let's take a look at what it means to optimize, right, our bundle. And so let's look at our Cobb-Douglas equation first, or Cobb-Douglas, not equation, but Cobb-Douglas indifference curve first. Cobb-Douglas, right? So some things that we know about Cobb-Douglas: the MRS is equal to the slope of the IDC at any given point along the curve, right? Now, some things that we know about the budget constraint is that the budget constraint is the rate at which we can exchange goods while still being affordable. And so what you'll notice is that the MRS is a ratio, it's a slope, and the budget constraint is a ratio, right? You can think of it as a slope. And so how we optimize is by setting those two slopes, or those two ratios, equal to one another. Okay, so say that I have this this budget constraint, right? So x1, x2, right? Let's say that this is 12, this is 6, indicating that the slope is equal to -1/2, right? And so say that I'm given a indifference curve that follows utility is equal to x1 times x2, right? So this is like the classic form of your Cobb-Douglas utility function. And so while I have you guys here, I want to kind of give you guys a quick shortcut as to how to find your MRS very easily, right? So typically you think about MRS equals marginal utility of good 1 over marginal utility of good 2. And so in this case, it's actually really easy to find your MRS. It's just the marginal utility of good 1, which is just x2, over the marginal utility of good 2, which is just x1. And so this is your MRS, right? Now think about more complex examples where you might have exponents. So say that utility is equal to x1 to the 1/4 and x2 to the 1/2, right? Now all of a sudden, taking the marginal utilities is a little bit more complicated. So we still can definitely do it, right? But it just becomes a little bit trickier. So we have 1/4 x1 -3/4 over x2 to the 1/2 over 1/2 x1 to the 1/4 over x2 to the -1/2, right? And you know, I think that if you have a decent math background, you can definitely kind of make this a lot easier for yourself, just by moving the x1 terms to one side and the x2 terms to the other side. So just in case you guys don't know, if you have a negative exponent, right, you can kind of just flip it to the top and make it a positive exponent. So this right here turns into 1/4 x2, and then because the 1/2s are being multiplied, or because the x2 terms are now being multiplied to one another, right, you just add the exponents. So this becomes positive 1/2 to positive 1/2. So it's just x2, so 1, I guess. over 1/2, and then you can do the same thing where you just add the exponents, so it becomes 3/4 plus 1/4. So x1, 1, right? And now we have x2, 1, x1, 1, and it's no longer complicated. You can just multiply through by 4, and you just get x2 over 2x1, right, as your MRS. And that's not too bad, right? But, you know, in a time-sensitive environment, it can be hard to do this, especially under pressure. And there's a lot of ways in which you can go wrong about doing this. Now, what I'll tell you is that there's a secret, and this applies to any sort of Cobb-Douglas. So if you generalize, and I'm going to use a different marker, if you generalize your Cobb-Douglas equation into u is equal to x1c, x2d, where c and d are the exponents, the MRS is just equal to c x2 over d x1, right? And this is just a mathematical trick that you can do. You can kind of just show that it's right. So it would be 1/4 x2 over 1/2 x1, which is what we have right here. So I would definitely recommend using this trick because it can save time, especially in a time-sensitive exam like these 10A midterms and finals are. Are there any questions about this in particular?
Yeah, where did you get the exponents from? The 1/4 and the 1/2?
Yeah, so this is 1/4 and this is 1/2, but it's just generalized as C and D because it works for any exponents. So I would definitely write that down. But yeah, so I kind of forgot what I was talking about. I went on a huge tangent as I always do. But this is definitely worth knowing. This definitely helped me a lot in the class. It just makes things a lot smoother. You're for sure going to get this right if you have Cobb-Douglas, and it just takes time away that you maybe would use correcting mistakes or something.
So for every problem, C and D will always equal 1/4 and then 1/2 respectively?
No, it won't always equal this. So C and D don't need to be 1/4 and 1/2. C and D could be 1/3, 1/3. C and D could be, I don't know, 7/8, 3/15. The beauty of what's going on here is that this applies to any number C and D.
Have to be between 0 and 1?
No, they don't even have to be between 0 and 1.
So you could have like 5/4?
Yeah, you could have 5/4. Mathematically, yeah, you can.
Okay,
So you can
thank you.
just choose any number for C and D?
Well, C and D will typically be given to you. So
Oh, okay.
in this case, the problem that I have kind of come up with on the spot, C and D are just 1 and 1, right? You see that?
Yeah.
Right? Actually, no, they're 1 and 1. I apologize. Yeah, they're 1 and 1. But if you were given this problem, that would be your level of C and D, right? So C and D are subject to whatever the problem gives you.
Okay. Thank you.
Yeah. So let's kind of go back to the problem at hand because I don't want to take up too much more of your time. So x1, right? So we're given this utility function. This is our MRS. And so how do we go about making sure that my slope is equal to my MRS, right? When we don't know what our optimal level of x2 and our optimal level of x1 are. And also, this kind of relates to what was talking about when I said it doesn't matter whether you make your slope negative or positive, as long as you're consistent. The reason why it doesn't truly matter is because of the fact that you're setting this negative slope equal to this negative MRS, and so the negatives are going to cancel anyways. You just want to make sure that you don't have one of them being negative and one of them being positive, because that'll definitely it'll mess you up. And so you just want to be consistent throughout the problem that if your slope is negative, then your MRS is negative. If your slope is just positive, then this is positive, right? They won't dock you. I don't think I ever got docked. But you know,
Any whole CP?
it might be best if you just made them both negative. But that's kind of what I was talking about, where it doesn't truly matter. So when I'm optimizing, given this information right here, right, what I said was you want to make sure that the slopes are going to be equal. Well, because we already know the slope of one of them, I'm going to set negative 1/2 equal to negative x2 over x1. And so this becomes really easy in that now I'm given that negative 2x2 is equal to negative x1, so that x1 is equal to 2x2. But this doesn't tell us much just quite yet, because if we don't know what x1 is, you don't know what x2 is, right? And so this is where having this constraints on our budget constraint is going to be able to give us a maximum, or not a max, an optimal value of x1 and x2, right? Because for now, this is just indicating the relationship between the two, right? It doesn't tell us about how many of each we have. So let's say that I'm trying to think of a situation in which I think 60, so let's say that m was equal to 60, P1 was equal to 5, P2 was equal to 10. I feel like I use these numbers all the time, but they work fine, so it is what it is. Now, because I have this information, I can actually write this down in the format of a budget constraint, right? So I have P1 x1 plus P2 x2 is equal to 60, right? I know what P1 is and I know what P2 is, right? So this becomes 5x1 plus 10x2 is equal to 60. And in addition to knowing this, right, I still don't know what x1 and I still don't know what x2 are, but I know what the relationship is between those two. And so you see how I have x1 is equal to 2x2? What I can do right here is I can actually sub this in for the value of x1 that's right here, so that I get 5 times 2x2 plus 10x2 is 60. This yields 20x2 is equal to 60, which means that x2 is equal to 3, right? And because I now know what x2 is, I know what x1 is effectively. X1 is equal to 6, right? And so you'll notice that this is the point right over here. This is 6, 3, right? And it's right in the middle of this curve. So one of the things is that if the exponents are the same for C and D, you're typically going to have a point that's going to be right between or right in the middle of this budget constraint. But that's not quite as important because you'll typically just be able to figure that out just anyways. Are there any questions about how I just solved that? This is going to be the standard procedure for all of these questions, so it's good that you're familiar with it to begin with. Okay. And there definitely will be instances in which you may be getting like harder numbers or something like this. But this is kind of a baseline of, so to answer your question, Stephen, this is given a budget constraint and given my comparison of preferences, X1 and X2, right? This tells us what the optimal bundle is, right, given my preferences. So yeah, that's kind of it for that. I wanted to spend the majority of the time talking about Cobb-Douglas. Next class, so Wednesday, we're going to talk about perfect complements and then perfect substitutes before we get into some numerical examples. But yeah, if there's no questions about this material.
Will we go for problem set 2?
Problem set 2 or extra problem set 2?
Problem set 2.
We can, although I think that your TAs typically post a video that should give a detailed kind of response to that.
Yeah,
So,
yeah, I remember the video.
So what I will say is that I won't go over all of problem set 2. But if there's still confusion about problem set 2 by Wednesday, I'm more than happy to go over questions. But they do talk about it in section and then they post a video. So I think you should have a good amount of resources to cover problem set 2, which is why I kind of want to focus my attention on, say, extra problem sets or maybe some midterm material. But
Cool. Thank you.
yeah, so it seems like there's some comments about just the problem sets. So just a reminder, I do have drop-ins right after. So starting at 2, what time is it? Yeah, starting at 2, I'll have drop-in. And then I also have drop-in tomorrow. And then obviously we have lecture on the Wednesday. Sorry, brain freeze. But yeah, so thanks again for coming, guys. I'll still be around for a bit just because I'm just going to be here for drop-in anyways. So feel free to ask questions. If not, enjoy the rest of your Monday.
So the marginal rate of substitution for this problem, that would be -half, right?
So yeah, yes, because of the fact
So
that
basically, for every x2, which is basically, in this case, the price of 10, you'd be getting 2x1, and x1 is the price of 5.
so I like kind of the way you're thinking about it, but remember the Cobb-Douglas is shaped like this, and I'll use a green. Cobb-Douglas is shaped like this, and so essentially the MRS is -1/2, but it's specifically -1/2 at this point right here, right? So it won't always be -1/2. Like it won't be -1/2 at this point, and it won't be -1/2 at this point.
Okay, so that's because you factored in the 6 and the 3, and you realize that 1/6 is equal to 2 3s.
Could you say that again?
And that's just because you factored in the 6 and the 3, and 1/6 is equal to 2 3s.
Yeah.
Okay.
So I guess what I will say is that the if you were to actually physically plug in 6 and 3 into these numbers or into these values right here, it would be the inverse of the slope. So you can kind of think about it that way. But I don't like to get kind of too technical into the relationship between slope and whatnot. I think it's just important to know that just the MRS in general is this and this, and how it relates to slope in general.
Okay, thank you.
Yeah, no worries. Oh, dude, my fucking back. Oh. Yeah, no worries, guys. You're welcome.
I came late to section on accident. What did you kind of talk about in the beginning?
I talked about preferences just in like as a whole. I talked
Just
about
like the 6 types of them.
yeah, like the different indifference curves, like what an
Okay,
indifference
yeah.
curve means and stuff. When did you get in?
Honestly, like in the last like 10 minutes, I came late.
Okay.
I took the quiz and then like I started making like food because it totally slipped my mind.
No worries. Well, I do record these, so
Oh, okay.
you're gonna be able to just kind of see through. I think if you download it, you can also go like whatever speed you want. Although I'm not too sure, but I posted it as an MP4.
And where do you post all this stuff? Like, is it on the Gotcha Space page?
Yeah, so it's on. You should be enrolled in the CLAS for 10A, and then
Yeah.
I have my own like individual tab along with the other 3 or the other 2 10A tutors.
So is
and
it on Gotcha Space or CLAS?
It's on Gaucho Space. So Gaucho Space has or I guess CLAS has a Gaucho Space page for the class that you're enrolled in.
Okay. Oh, I think I know what you're talking about. Yes, CLAS Econ 10A fall.
And then you should be able to see my tab, and then my tab should already have 2 lectures posted. So this will just be the 3rd one that's posted.
Oh yeah, Eriking. Yeah, because I came to your first one. Oh, the extra PS2.
Yeah.
Or that was last Wednesday.
That was last Wednesday.
Okay, so you're gonna post this one up.
Mhm.
Okay, sweet. Thank you.
Yeah, no worries.
All right, sweet.
All right. Any other questions?
What is the difference between like Cobb-Douglas and is it just like finding those like slopes?
Well, Cobb-Douglas basically just implies that it's continuously a diminishing marginal rate of substitution. And diminishing marginal rate of substitution, sorry for speaking so fast, just basically says that the slope goes from like steep to not steep, right? So as I move along this axis right here, the slope is actually going to be smaller in magnitude.
Right.
Yeah.
And then they like, I was looking in the lecture that it's the tangent line closest to 0 is like the true MRS, or like as close as you can get.
Yeah, so the reason why is because if you think about this budget constraint, right? This budget constraint basically just implies that we're at the cost that we want to be. So you think about all the different indifference curves that we have.
Yeah.
This is an indifference curve as well.
Oh,
and
wait.
this is
Real
an
quick.
indifference curve as well. So we have
Yeah.
infinitely many indifference curves, but only one of them is tangent, right?
Yeah.
This one doesn't touch our budget constraint. Keep going. Sorry.
Yeah. Is the tangent line of like the indifference curve the budget constraint?
Yeah. So it's where the slopes are equal. Yeah. So this is
And
the
that's
budget constraint.
like, so the midpoint of like the points
Budget
given
constraint.
on the equation, like the midpoint of that budget constraint will be the tangent line to the indifference curve.
Yeah, and yeah, it's not necessarily going to be the midpoint necessarily for all questions, but it is in this case.
Okay.
So this is the point of tangency.
Okay. And it won't always be on that midterm. It could be anywhere along the line.
Yeah, it kind of depends on the utility function that you're given.
Okay. And then, so for this one, like, how did you figure out it was 6-3? So I saw you did like, you do a 1x2 and a 2x2, and then you multiply that to equal each other and then solve from there.
So yeah, you find the relationship between x1 and x2 when the slope is equal to the budget constraint slope, right? So I set it equal to the slope of the budget constraint right here. And once I find this relationship between x1 and x2, I can plug it into my budget constraint right there.
That makes sense. I like that. That seems a lot easier than, that's pretty good.
All right. Does that answer your questions?
Yeah, that does.
All right, awesome.
Okay,
Thanks
sweet.
for
Thank
coming
you. Yeah.